So I'm going to go ahead and show you guys how to do example 3 on page 11 in the chapter 9 lecture notes. So this table shows the scores for 14 students the first 2 times they took the verbal SAT. At alpha equals 0.01, is there enough evidence to conclude that the students' verbal SAT scores improved the second time they took the verbal SAT? So is there enough evidence to conclude? So this is going to be the claim. Students' verbal SAT scores improved the second time they took the verbal SAT. If they improved the second time they took the SAT, that means that they got better scores on the second time they took the SAT, which means that these numbers have to be bigger than the ones in the first column. That means that the ones in the first column are less than the ones in the second column. So we're going to use this later to write out the claim, the opposite, the null hypothesis, the alternative, and so on. So for the, actually, let's go ahead and do it right now. So the claim is that the average they got in the first time that they took the SAT was smaller than the average score they got when they took it the second time. So mu1 is less than mu2. But because this is dependent data, it's the same person taking it twice, that means it's dependent data. So the notation that I need is going to be the one with the mu d. So I need to subtract mu1 minus mu2 is less than mu d. Sorry, mu1 minus mu2 is less than 0. Then replace the mu1 minus mu2 with a mu d. So that means that mu d is less than 0. So the opposite of this claim is that mu d is bigger than or equal to 0. That means null hypothesis is mu d is equal to 0. Alternative hypothesis, mu d, you copy the statement that does not have an equal, so the first one, mu d is less than 0. And the claim in this case was a less than 0. That means that the claim is in the alternative hypothesis. Second step is to find the test statistic. Now for this one, the test statistic is t equals d bar minus mu d over sd over square root of n, where s of d is equal to the square root of n times sum of d squared minus the sum of d being squared divided by n times n minus 1. So let's go ahead and go and find the d squared, and we're going to go and find the d column also. And we're going to need the d column also because we need to find d bar. So let's go ahead and find the d column. So in order to find the d column, we need to go ahead and subtract sample 1 information minus sample 2 information. So it's always in that order. So again, this is sample 1 minus sample 2. And then for the d squared column, we're going to go ahead and square the d's. So again, for the d squared, we're going to square these numbers. And let's go ahead and do the calculations for the d. So you're going to go into stat, and you're going to go into edit. I've already loaded all of my numbers into my graphing calculator, so you might want to stop the video here and then plug in the numbers into your calculator. So for L1, I put in the score on the first SAT, and then for L2, I put in the score for this second SAT. So let me label these two. This is L1, and this one was L2. Then under L3, I'm going to go and put the differences. So the difference again is sample 1 minus sample 2. Go up to the L3, go to second, and then L1, minus, and then second, and then L2. And that's going to give me back all of these numbers. So I'm going to pause it, write out the numbers, and then I'll come back. Alright, so once we have all of our numbers for the d, we're going to take this column and we're going to square it to find the next column, which is a d squared column. So because L3 was a d, in L4, I'm going to go ahead and square the L3. So let's go to L4. So go up to the L4, go to second, and we're going to square the L3. So go to second, L3, and then square this, and it's going to give me these numbers. And again, I'm going to go ahead and write out these numbers on the table. Alright, so once we find all of the values under the d squared, we're going to go ahead and go back to the formula. So the two formulas that we have are the one for the t, which is a t distribution, and the standard deviation of the differences. So we're going to need n times the sum of the d squared minus the sum of d being squared, and then divided by n times n minus 1. So in order to go and find the sum of the d squared, we're going to go ahead and add up the d squared column. In order to find the sum of the d, we're going to add up the d column. So let's go ahead and do that. So the D column was under L3 and the D squared column was under L4. So let's go ahead and go to second, go to quit. And so that means we're going to go to the home screen, go to second, go to catalog. So the catalog is on the 0, and then go down to the sum. So go to the T and go up to the sum, or go to the S and go down to the sum. And we're going to take the sum of the L3 column, so second L3, and that gives me negative 472. So that means that the sum of the D, sum of the differences, is equal to negative 472. And then we're going to go and find the sum of the D squared also, because we're going to need that as well. So again, second catalog, or you can go to second, enter, and then replace the L3 with an L4. And that gives me back 38,000. So sum of D squared is 38,882. So we're also going to need D bar. So let's go ahead and find D bar as well. D bar is equal to the mean of these differences. So either you add them all together and divide it by the number of values, and here we have 14 values, so negative 472 divided by 14. So negative 472 divided by 14, and that gives me negative 33.7143. 7143 because we used 4 numbers after the decimal. Or you can go to second, go to catalog, and go to the mean. So go down to the M, and then to the mean, and we're looking for the mean of the difference column. The difference column was L3, so go to the mean of L3, and that's going to give me back negative 33.7143 as well. So D bar is equal to negative 33.7143. So we're going to go ahead and use these numbers and plug them into the standard deviation of the difference formula. So we said that n was equal to the number of values. We said that was equal to 14. So plug in a 14. So square root of 14 times sum of the difference squared, that's 38,882. So 38,882, and then minus sum of the difference squared. So sum of the difference is negative 472. You take negative 472 and you square this, divided by n times n minus 1. N is 14, n minus 1 is 14 minus 1. So if you have a scientific calculator, do the top and then write it down, do the bottom, write it down. So let me show you what you would do if you have a scientific calculator. So you take 14 times 38,882, and then minus, put in parentheses negative 472, and then squared. And then this gives me back 321,564. So that goes in the numerator, inside of the radical. So 321,564 divided by 14 times 14 minus 1. So basically 14 times 13, and that gives me 182. So if I simplify this, I would take second square root 321,564 divided by 182, and that gives me back 42.0337. So if you have a graphing calculator, you can just go to second, go to catalog, go to standard deviation, so go to the T, and then go up to STDDEV, and press enter. Then we're going to find standard deviation of the difference column. Difference column was under L3, so go to the L3, and that gives you the same answer, 42.0337. So that means standard deviation of the differences is 42.0337. So go ahead and plug it into this formula for the test statistic. D bar is equal to, we found that it was negative 33.7143. So negative 33.7143 minus mu d. Mu d is equal to 0, so it's based on the null hypothesis. This becomes a 0, so minus a 0. You don't actually have to write down that minus a 0, divided by SD, 42.0337, divided by square root of n, so divided by square root of 14. So when you put it into the calculator, don't type in that minus 0 and put parentheses before the 42 and after the radical 14. So it would give me negative 33.7143 divided by, again, parentheses before the 42.0337, divided by square root of 14, and then close the parentheses at the end. And that gives me a negative 3.0011, and so on. So this gives me a t. That means that I only need 3 numbers after the decimal. So it's negative 3.001. So for the third step, or actually in the second step, the test statistic is negative 3.001. And then for the third step, we're going to go ahead and find the rejection region. So the rejection region, because it's a t-distribution, we're going to go ahead and use the traditional method. So in the traditional method, we're going to go ahead and plot our distribution. So it's a t-distribution. And then we're going to go ahead and shade the corresponding area. So this is a less than sign, we shade to the left. And in the traditional, this area to the left is alpha. So in this example, it says at alpha equals 0.01. So we want to go ahead and plot alpha equals 0.01. So alpha equals 0.01 is the area to the left. And we're going to go and find this cutoff here. But if we look in the t-distribution, so this t-distribution has the area in one tail of 0.01, but it also has degrees of freedom. So let's go back and find degrees of freedom. Degrees of freedom is n minus 1. N is equal to 14, so 14 minus 1 is equal to 13. 13 degrees of freedom, area to one tail of 0.01. So area of one tail of 0.01, degrees of freedom we said was 13. Go down and go across, and that gives me a 2.650. But this is if it was a positive number. So if it was on the right side, it would be positive 2.650. But because it's on the left, we put a negative 2.650. So this is negative 2.650. And we're going to go ahead and plot our test statistic, negative 3.001, against this critical value. So negative 3.001 is to the left of that negative 2.650. It's in the shaded region, so we do reject. So in conclusion, we're going to reject the null hypothesis, and if we reject the null hypothesis, there is sufficient evidence to, and in this case the claim is an alternative, so we can say support the claim, and we're going to go ahead and copy out starting from conclude. So actually starting at that, the claim that students' verbal SAT scores improved the second time they took the verbal SAT. And this is based on alpha equals 0.01. So we're going to go ahead and write out the claim that students' verbal SAT scores improved the second time they took the verbal SAT. And this is based on alpha equals 0.01.